All right, so I just wanted to make sure that you had access to the rest of the material for Chapter 16 that you'd be responsible for. You might notice as you look at the homework, there'll be some material that we didn't really cover in class. So I wanted to make sure that I did that for you, and that's what this video is all about. So where we stopped the last day of class that we had lecture was we introduced this idea of the instantaneous center of zero velocity. And the idea is that if there's a point on an object, and it turns out it can be off the object as well, where the velocity of that object is zero, you can actually figure out the velocity at any point on the object, any other point, using the fact that, for instance, the velocity of the other point, let's call it v sub x, is equal to the velocity at the instantaneous center, which of course is 0, plus omega of the object, plus crossed with the position of point x with respect to the instantaneous center. So this is really that relative velocity expression that we used in the previous section, except that this is equal to 0. And so the things that we know is that the magnitude of this velocity is simply the angular velocity of the object times that position vector, just the magnitude of it, and that the velocity vector that we're looking at is perpendicular to the radius, which is what is shown in this picture right here. All those velocity vectors were simply drawn by going to that point and then drawing a vector that was perpendicular, and that would be to the radius, and that would be the velocity vector. So for instance, and we can use that fact actually to figure out where the instantaneous center is. So here we have this board propped against the wall, and we know that it's going to slide down the wall. So we know that point B, which is along the wall, is going to eventually have a velocity downward, and we also know that point A, which is on the floor, is going to slide out. So if we want to find a common center point, we draw lines that are perpendicular to that velocity, and we just extend them until they intersect, and that becomes our instantaneous center. Then these become the radii that we use. So this would be the radius of B with respect to the instantaneous center, and this would be the radius of A with respect to instantaneous center. And then those velocities would just be equal to, I'm going to do magnitude, the omega of the board times those radii. And so it becomes really easy to find velocities if we know those radii, or sometimes this is going to be a way that we could figure out what the omega is. It just depends on the particular problem. So just, so the idea is, again, just to repeat it, that we're trying to find a body on a point on the plane of motion where the velocity is 0, and it can be on the object or it might be off of the object. We just saw an example where it was off the object. And if we figure out this location of this point, it's really easy to find the velocity of a point, because it's just, the velocity is just equal to the angular velocity of the object that we're looking at times that radius vector. And it's just easier for us to find these values. Let's look at this example, which I kind of started in class, but I'm worried. Yeah, so let's do with some sort of bright. So for instance, here I have 2 points that are moving. I have this velocity of D, and I have velocity of B right here. And so now I'm going to use this to figure out, first of all, I'm going to work with the piece BD, and I'm going to try to find the instantaneous center of that point. And the way I'm going to do it is extend a line from each of the velocity vectors, so it's perpendicular, and they're going to intersect at a point, and this is the instantaneous center. Now, I want to know, basically then, if this is r of b with respect to IC, and then this is r of d with respect to IC, I can write both of those velocities, vd, is equal to omega bd times that length of that radius, and also I can do the same thing with b. Now, the geometry here helps me out because I already know that angle is 45 degrees, this angle is 45 degrees as well, and this is a 90-degree angle. So the length of this side is the same as the length of BD, which is 0.4. And because this is the hypotenuse, this is going to be 0.4 times the square root of 2. So what I start off with is I go, hey, I know the velocity of D, it's actually 3 meters per second. And that's going to be equal to the angular velocity of that piece BD times the radius, which I just found was 0.4 times the square root of 2. So I can find the angular velocity of this piece BD, and it turns out to be 5.3 radians per second. Now I can use that, and it can help me find out the velocity of B. So now I know that this is 5.3 radians per second. I found the radius was equal to 0.4, and so I find that the velocity of B turns out to be 2.12 meters per second. Now I also notice that I could say calculate the velocity of B could also be written as the angular velocity of the piece AB times the radius that goes from A to B. Because B is a pin, and so it's attached actually to the two different pieces, the piece AB and the piece BD. And so now I know that the velocity of B I just found was 2.12, and that's equal to omega AB, which I don't know, times the length of RAB, which is 0.4, and now I can find AB, and that actually ends up to be exactly the same as the omega of BD. So the instantaneous centers would be kind of easy to use. I thought I'd do another example that's a little bit more involved. So we have this one right here. So we're saying rod CD is rotating with an angular velocity of 4 radians per second. It's counterclockwise. And we're trying to find the angular velocities of rods AB and BC. So for one, I know that if DC is rotating the way it's shown, point C is going to have a velocity vector that looks like that. And I also know that, thinking about as it goes, the velocity of B, because what's going to happen is as CD rotates counterclockwise, it's going to push AB to rotate clockwise. And so I know that's going to make B, point B, move in the way that I just showed. Now, in order to find the instantaneous center of these two places, well, first of all, I can find the velocity of C I already know, so I'm going to figure that out. Just velocity of C I can actually find because point D isn't moving, so it's just equal to omega CD times 0.5, which is 4 times 0.5, which is 2 meters per second. And then I'm going to actually, now I'm going to find the instantaneous center for these two velocities, because I want to use that to help me figure out what would be the angular velocity of the piece BC. So I'm going to extend a perpendicular like here, and then extend this, and this is where they're going to intersect, where this angle right here would be 30 degrees. Now, I know that this side, so I have this right triangle here. I'm going to just kind of try to outline it so we can see it. Here's my right triangle that I'm focused on, and this is my instantaneous center. Now, this side, of course, is 0.4. I want to figure out what the, now, if this would be the radius, I would use, this is the radius of C relative to the instantaneous center for point C, which is this right here that I already labeled. And so I could write the velocity of C could be, I could write it as the omega of BC times the radius of C with respect to the instantaneous center that I found for points B and C. Now I need to know what that value is of C. And so what I'm going to say is the tangent of 30 degrees is going to be that length of that piece of the triangle over 0.4. And so this ends up to be 0.4 times the tangent of 30 degrees, and that ends up to be 0.231. So that's the length of that radius. I'm going to use this in here, and so the velocity at point C, I already found it. It's true regardless of what reference point I use. It's equal to omega BC times 0.231, and omega BC is then equal to 8.66 radians per second. Then I can find the velocity of B using omega BC times the radius for that one, which is this, the length of this hypotenuse really, which is going to be the 8.66, and then the radius is going to be, I can find using the Pythagorean theorem, and I find that that velocity is 4 meters per second. So okay, so now I found the velocity of B, and I found the velocity of C. Through that, I was able to find the angular velocity of BC. I did that, but this is what I need to do next. So I'm going to need to go on to the next. So I had said that the velocity of B would look like this, but now I'm thinking about the omega AB. Now on the previous slide, I had found that the velocity of B, the value of that was 4 meters per second. Now I want to write it as in terms of the angular velocity of this piece right here, AB, times the radius of B with respect to A, and A is just 0, so we don't really need to worry about it, as that is a relative velocity. So this is just equal to omega AB times 1 is equal to 4 meters per second. So omega AB turns out to be 4 radians per second. And so those are two examples of using the instantaneous centers. So the last I wanted to talk about is, you know, we did all these relative motion analysis with velocities, but what about acceleration? So if we used our expression, so we said the velocity of B was equal to the velocity of A, plus a term that gave us the relative velocity of b with respect to a. To do the acceleration, we just want to take the time derivative of that. And so it's going to give us the acceleration of b is equal to the acceleration of a. But now, this time we have two different terms for the acceleration of b relative to a, because there's two possibilities. It can have a tangential component and a normal component. You know, the tangential component is due to the fact that the actual linkage might be rotating with an angular acceleration, and so that's given us a tangential component. But then the normal component is simply because it has an angular velocity, and that's the normal component. So we have these two components. And then, of course, there could be, you know, the acceleration of a is just if the linkage itself is translating. The other two terms are due to rotation. So the way that we write this is the tangential acceleration. This is the tangential term, which is the angular acceleration times the radius. So that makes sense because we've seen that relationship before, that tangential acceleration is equal to the angular acceleration times the radius. And then this is the normal component, which is really, it's just the centripetal acceleration. So it turns out that, you know, for velocities, just to remind you, we had the velocity of a. To find the velocity of b, we would use the velocity of a, and then the term that described the velocity of b relative to a was due to the angular velocity of the actual piece times the crossed with the position vector of b relative to a. And so you can see that this acceleration term is a little bit more complicated because it has those two terms to give the two components of acceleration. So for this one, we're going to look at a relatively simple example. This is, again, the roller, which we had done previously. But we're going to say, so we know that point A has an acceleration downward of 5 meters per second and a velocity of 6 meters per second. And so we want to figure out what is the angular acceleration of this rod as it's falling and the acceleration of b at that instant. So let's take a look at this. I have the acceleration of b is equal to the acceleration of a plus the angular acceleration of AB crossed with the position vector of B relative to A minus omega squared of AB times the position vector of B with respect to A. So now we actually don't know a couple things here, but we do know the instantaneous center, and we could actually use the instantaneous center to find the omega of AB, because we know the velocity of A is 6 meters per second, and that's going to be equal to, if we use the instantaneous center, it's going to be equal to omega AB times the position of A with respect to the instantaneous center. Now, if we look at the geometry here, we know that, I think we're having trouble seeing this, but this is actually 4 meters over here. I think it got cut off. So this is 4, the hypotenuse is 5, so that means that this is 3. So the radius from the instantaneous center is actually 3. So we have 6 meters per second is equal to omega AB times 3. So omega AB is actually equal to 2 radians per second. And as this rotates, it's going to rotate this way. and that's going to be in the positive z direction. So we needed to know that. So let's start to try to write these things in. So acceleration of b is equal to acceleration of a, which is minus 5 in the j hat direction, plus alpha ab is going to be in the k direction. I think it's going to be positive k because it's going to accelerate in the counterclockwise direction. But if I'm wrong, it's okay. My alpha will just come out to be negative. The position of b relative to a is it's 3 over in the x direction and 4 down in the y direction. And then omega AB is 2 squared, and again times 3I minus 4J. So this is the expression I get for the acceleration of AB. So I do have to do the cross product. Let's do that. K cross I is going to give us J. K cross J is going to give us minus I, but there's a minus sign there, so that gives a plus. So it's alpha AB times 4I minus 4 times 3 is 12I. 4 times 4 is 16, and that's going to be plus 16J. All right, now I want to collect my x and y terms. In the x direction, I get 4 alpha AB minus 12 and in the y direction I get 3 alpha AB minus 5 plus 16, which ends up to be 4 alpha AB minus 12 in the I direction plus 3 alpha AB plus 11 in the j direction. So this is my acceleration of b, and you might say, well, I don't know, I don't have a number for that because I don't know what alpha is. So let's think about this. I'm going to go to the next page. Let me just make sure I got that right because I didn't have it all written down. I think I do. Yeah. Okay, so one of the things we do know is when B moves, it's going to move in this direction and it's going to accelerate in this direction. So this has to be equal to 0, and that becomes the way that we can figure out the angular acceleration of that AB. So 3 alpha AB plus 11 is equal to 0. Alpha AB is equal to minus 11 over 3, which is equal to minus 3.67 radians per second squared. And that means it's going to be in the clockwise direction. So, which is not what I expected. Now I can substitute this in here to find that acceleration, which is in the x direction. And I get the acceleration is minus 26.7 meters per second squared in the I hat direction. And I think that's right. It doesn't seem right, but hopefully that's right.